Great. Great. So today I'm introducing today's CIQC Colloquium speaker, and it's Michel Devoret from Yale, who will be talking about quantum error correction in a superconducting cavity. So far in this CIQC Colloquium series, we've heard a lot of talks about quantum computing with atoms and ions, but of course the results that Michel will present today were performed on very different hardware used for circuit quantum electrodynamics. This is also a highly promising platform for quantum computing applications. So in this intro, I'll be kind of providing some background material to supplement the ideas in Michel's talk later. So I'll go over the hardware that goes into making these circuits at a very high level. And I'll also briefly discuss how to visualize some of the entangled photon states that can be generated in these experiments. So the hydrogen atom provides a textbook example of a very understandable quantum degree of freedom. And this is the single valence electron. Atoms are kind of a very natural qubit because they come with quantized energy levels from which we can usually choose two to form a qubit. And another nice property of atoms is that nature basically provides these microscopic identical qubits for free, although you do need to trap and cool them in ultra-high vacuum for quantum computing applications. On the other hand, the superconducting qubit as a quantum object is quite different because it's fabricated onto a chip, and the quantum degree of freedom is a macroscopic superconducting condensate that sloshes back and forth amongst circuit elements. So it might seem somewhat surprising at first that such a system can act as a quantum object, but of course it's well known for some time and experimentally proven many times that the flux and charge in the circuit satisfy the same canonical commutation relations as position and momentum operators. So the mapping between these two systems is that we're kind of taking this microscopic degree of freedom of the electron and mapping it onto the sloshing behavior of this macroscopic condensate. Besides the fundamental differences in the state of matter and the quantum degrees of freedom in these two systems, we can compare a few other quantities of interest. To address the atom, we typically use optical frequencies, but the circuit is controlled using microwave frequencies. And at the moment, superconducting qubit quality factors are somewhat amazingly roughly comparable to the 1s to 2p transition in the hydrogen atom. The figure of merit where we actually see a large difference between these two systems is in the dipole moment, which kind of quantifies how well you can couple this qubit to the light field. And in the superconducting system, the dipole moment is about 30 million times larger than in the atomic system. So it's this absolutely gigantic atom-like coupling that's actually enabling the possibility to explore very rich physics in these systems, as well as the possibility of fabricating and designing these systems to meet very specific needs. So the basic ingredients in the circuit QED platform are microwave resonators and superconducting qubits. So the resonator can simply be thought of as a harmonic oscillator with some resonant frequency omega r. And the qubit Hamiltonian contains, in addition to just the normal harmonic oscillator term, a Kerr nonlinearity, and this increasingly shifts the energy levels of the bare harmonic oscillator. So the overall effect of this is that the transition frequency between, for example, the 0 and 1 levels of this oscillator are not the same as the transition frequencies between 1 and 2, 2 and 3, and so on. And this nonlinearity makes it possible to isolate only the 0 to 1 transition and obtain an effective two-level system. Here I've put transmon in parentheses because the transmon qubit is a very common type of qubit, and Michel will be, that's the experimental platform that is relevant to Michel's talk, but there's also many other designs that work. So in its simplest conception, a microwave resonator is simply a metal box. In practice, there are much better designs, such as this quarter wave resonator, and these are much better suited for producing long-lived single photon states. So this cavity is basically a coaxial geometry, and it consists of like cylindrical walls with a central post, and it's shorted on the bottom. So this region here at the bottom defines the cavity area. You can see the electric field lines indicated by the blue arrows. So these cavities are designed to accommodate microwave frequencies, roughly in the vicinity of 5 to 15 gigahertz. And these frequencies are nice because it avoids any complications due to thermal photon population of the mode at the millikelvin temperatures used in these experiments. But they're still low enough that it's actually convenient to also control the system using off-the-shelf RF electronics. And dissipation is minimized in the system by actually making the cavity from aluminum. And then, of course, at these millikelvin temperatures, the aluminum is superconducting. So this cavity basically defines a very long-lived mode of the electromagnetic field. And depending on the cavity design, the photon lifetime inside can range from hundreds of microseconds to on the order of milliseconds. Okay, so the second main component in the system that we need is this qubit. And as I stated earlier, the qubit is formed by this low energy 0 to 1 transition in the anharmonic oscillator. So the nonlinearity is provided by a Josephson tunnel junction formed by two superconductors with a thin insulator in between. And this object can be modeled as a nonlinear inductor in parallel with shunt capacitance. So this X typically denotes the tunnel junction. And for this tunnel junction, it turns out that the current is periodic in units of the magnetic flux quantum phi naught. And the flux is just defined as the time integral of the voltage across the junction. But of course, by contrast, for a regular inductor, the current is linearly proportional to the flux. So from this relationship between the current and the flux, we can kind of start to see that the potential energy is actually also periodic. So instead of a harmonic oscillator potential, the stored energy in this object is actually a cosine. And this provides the required nonlinearity to make a qubit. Now, of course, we want to actually combine these objects into more complex circuits. And the circuit Michel will talk about today consists of two resonators with a transmon qubit coupled to both of them in this central area. So just to give you a rough idea of how these look and a sense of scale, this is an actual picture of the microwave cavities. You can see here these two cylindrical hollow areas, as well as the transmon qubit that's stuck in between them. And then, of course, the whole thing is cooled down to very, very low temperatures in this dilution refrigerator. And as an experimentalist, I just wanted to show this beautiful complex apparatus. Okay, so as we're combining the resonators and the qubits, there are kind of two broad ways that we could think about doing this. We could either think about the qubits as being kind of the quantum degrees of freedom of interest and entangle them and make interesting states, and simply use the resonators to couple the qubits or to perform readout. And we can also flip this around and look at it the other way and actually do cool stuff with the resonators while using the qubits simply as ancillas to control the resonators. And in his talk today, Michel will actually be working in this second kind of paradigm. So why exactly would you want to make entangled states in the microwave cavity instead of using the transmine qubit? Well, the cavity actually has much longer coherence times. There is a quite large state space that's very easily accessible just by adding more photons, which is a lot easier experimentally than physically adding more transmine qubits to your chip. And there's also a very simple error model that's involved, which is basically the loss of photons, and you don't have to think as much about dephasing. So these are some of the motivations for why you might want to try and create entangled states of photons in the microwave cavity and apply them to the problem of performing quantum error correction. So now I want to move on to a slightly different topic, but which will still hopefully be useful for understanding Michel's talk, which is how we actually visualize and understand these entangled states. So I'm going to start to think about a harmonic oscillator in phase space. And for a classical harmonic oscillator, we usually think about its state as just being a point with some particular x and p at time t. And for some ensemble of oscillators, one could think about a probability distribution in this phase space, which tells you the likelihood of finding a particle at some point xp at a particular time. Now, of course, if we try to represent a quantum state in the same way in this phase space, we run into a problem because position and momentum are non-commuting observables. So you can't express the state of a quantum harmonic oscillator as a point in phase space because this would violate the uncertainty principle. Okay, so kind of intuitively, if I'm trying to get around this problem, I could say, well, I'm not going to represent the state of my quantum harmonic oscillator as a point, but rather as a blob with some size that's determined by the uncertainty principle. And indeed, for a coherent state of a quantum harmonic oscillator with amplitude alpha, this is precisely how the quasi-probability distribution looks. And this quasi-probability distribution is called the Wigner function. Okay, so we can represent a general state of photons in the cavity in this phase space picture. So here I'm just showing some Wigner functions of typical states that Michel may also show later in the colloquium. So here we can see the coherent state of, the Wigner function of a vacuum state, a coherent state, which is simply displaced with some non-zero amplitude from the vacuum, and a squeeze state. So just by looking at these plots, we can see how the Wigner function kind of usefully gives us an indication of the average field amplitude as kind of the distance of the state from the origin, as well as the shape of the quantum noise of the state. And what I mean by that is you can see here for the coherent state, the blobbiness is symmetric in x and p. And you can compare that actually to the squeeze state, which has a reduced noise in one quadrature at the expense of the other. So we need to keep the area fixed to satisfy the uncertainty principle. And just based on looking at this Wigner function, you can actually gain a lot of intuition about the state. And for example, you can see here why the state is called a squeeze state. So if we look at the Wigner distribution, for example, for a single photon Fock state, we see a key property that makes the Wigner function a quasi-probability distribution instead of a true probability distribution. And that's the fact that the Wigner function can actually be negative. And a simple way of seeing why the Wigner function is actually negative for this single photon Fock state is by expressing it as the expectation value of the parity operator in a state that's displaced by some coherent state amplitude alpha. So I guess it's not super transparent how to compute in your head the exact value of the Wigner function at all points in phase space, but it's very easy to see that at the origin, we are expecting to obtain a negative value of the Wigner function for the single photon Fock state. Another example of a very quantum state that you can make in these microwave resonators is a cat state, which is a coherent superposition of coherent states at positive and negative alpha. And again, you can kind of see this characteristic negativity of the Wigner function, which is caused by these interference fringes between these two different cat states. And in general, I like to think about kind of characterizing the quantumness or entanglement in a state by whether or not there's negativity or how small the size of the features is in this phase space representation. Okay, so that concludes the intro, which hopefully provided some useful background information. And we'll now move on to the main event. So Michel is going to be presenting this talk on error correction in a superconducting cavity. And he performed his graduate work in molecular quantum physics at the University of Orsay and received his PhD from Paris University in 1982. And then he actually spent 2 postdoctoral years working on macroscopic quantum tunneling with John Clark here at UC Berkeley. And he continued this research when he returned to Saclay, where he started his own research group. In 2007, Michel was appointed to the Collège de France and taught there until 2012. He has too many prizes to list them all, but among them are the John Stuart Bell Prize, which he received jointly with Rob Schoelkopf in 2013, and the Fritz London Memorial Prize. He joined the Department of Applied Physics at Yale University permanently in 2002. And in his research there, he now focuses on phenomena such as quantum error correction, fault-tolerant quantum operations, and remote entanglement in superconducting tunnel junction circuits, which we will now learn about.
Okay. Well, I would like first to thank the organizers of this meeting for inviting me, and particularly I would like to extend my thanks and congratulations to Emily that gave a beautiful introduction to this to the talk I am going to present. I have now 2 challenges: explaining my experiments and then doing better as well as Emily in pedagogical explanations. So I hope you won't be too disappointed. I'm going to share my screen. It's always a little, there's always a bit of suspense here. Okay, so I think you should be able to see my title slide.
Looks perfect.
Is it really working?
Yep, it's working perfectly.
I don't see the usual the green surrounding, but I suppose this might be okay. So sorry, do you mind if I just redo this maneuver again? I'm a little bit surprised by the what's happening here. Okay, now it looks normal. Okay, so the purpose of my talk is, as Emily explained, to present the work in my group on error correction. And error correction right now is very important in quantum information, since we want to really prolong the lifetime of qubits, and so that we can do as many operations as possible in the amount of time they are living. And right now they are living a pretty short time in more or less any platform, so that you cannot do many operations coherently. And quantum error correction has this goal of prolonging the lifetime of coherence as much as needed to complete an interesting computation. So let me present my group, the people that have done the experiment I will be presenting. So the data has been taken by Alec Agbush here, Stephen Touza, and Philippe Campagne, who is here. By the way, do you see this mouse? Okay, great. Yep. I'd like also to acknowledge Rob Scholkopf, that has been mentioned by Emily, and Steve Gervin and Leonid Glassman, who are my senior colleagues at Yale, with whom I have collaborated over the years, and who played also an important role in all the preliminary experiments that were needed to achieve error correction. So my talk will be divided into 3 parts. I will, in the first part, I will explain this problem of correcting errors and the challenge it represents. Then I will introduce this grid state encoding, also called the Gottesman-Kitaev and Prescale code, that is really a wonderful invention, even though it took near 20 years to realize it. And then I'll go, thanks to the introduction of Emily, I will be able to go into the experimental setup rather quickly, tell you about the result, and then I'll discuss the future. Okay, so I think you're all familiar with this idea of a block sphere representing a qubit, which you can view as an effective spin. And this effective spin is subject to 3 independent noise processes, which you can understand as random fields along the orthogonal X, Y, and Z directions. And this is the problem of error correction, is to preserve the coherence of the qubit in presence of these noisy error channels. So as an introduction, let me explain the strategy. So we're going to use entangled states, and more precisely non-local entangled states. But let me just briefly explain what we can achieve with non-local wave function. So suppose you have a particle here, which is represented by this yellow ball here. Sigma denotes the extent of its quantum fluctuations. And we're going to put this particle in either one of 2 boxes, the blue box on the left or the red box on the right. And we say that this is a non-local situation because the 2 boxes are separated by a distance which is much larger than the fluctuation in the wave function. So we get this, this non-local, so-called non-local wave function, which is a superposition of the particle being on the left or on the right. And it turns out that the 3 attacks, 3 noise channels can be reduced to 2 processes. All these 3 independent channels can be reduced into combinations of bit flips, which is theta going into theta plus pi here, or the phase flips, which is the phase of the superposition phi here going into phi plus pi. Now you can immediately see that since local forces can only induce phase flip, local forces cannot move the particle all over this distance d, but it can change the energy at location blue or location red, and therefore it can wobble the phase. But at least we would say here that the bottle is half full and not half empty. We've been able to correct half of the processes, the noise processes. So how can we do both? How can we create an encoding which is fully immune to all local noises? Can we store the bit information non-locally? And as an icing on the cake, can we also at the same time store the phase information non-locally? If we can do both, then we will have protected the qubit entirely. And there are two strategies. So this was presented by Emily. I'm rephrasing a bit what she said. So we can, there are essentially two lines of answer to the problem of quantum error correction. We can either have a set of physical qubits, so all these spheres here represent physical qubits, and by adding sufficient qubits, we can create a large Hilbert space, which has the redundancy needed for error correction. And this is the strategy behind what is called the STIN code or the surface code, the color code. You've heard about these codes. And this is something that has been implemented at essentially at Santa Barbara. And at Google. Now, there's a sort of different strategy which is based on, this is the so-called continuous variable strategy, although it is better presented, as Emily has done it, as the consideration of the states of an harmonic oscillator, which essentially form a ladder. And the advantage of this Hilbert space is that besides the fact that there is potentially many states, there is only one error channel, which is photon loss. That's a huge improvement against the other strategy, which has 3 error channels per qubit. And examples of the kind of code you can use is this GKP code that was invented 20 years ago. So the difference between these two strategies can be summarized in the following 2 sentences. So here on the left, you have a large overhead, and you need a 1 Josephson circuit per qubit. But on the right, you have a minimal overhead because you have only 1 Josephson circuit that is needed for operation. So qubits here, physical qubits serve as ancillas here. They are not the place where the quantum information is stored. So let me explain the problem with the discrete register implementation. So if we take the STIN code, which has 7 physical qubits, we have a Hilbert space with 128 states, and the logical states, 0 logical and 1 logical, are entangled states of all the qubits. And this entanglement is quite subtle, but you can get a glimpse of how it is done by looking at these plaquettes here. So the 7 qubits have been arranged as a sort of hexagon, but it has 3 plaquettes. And you can notice that around all the plaquettes, the number of 1s or 0s is even. In practice, the feedback circuit that will correct this code is rather complicated. So you have these 7 qubits here, which are these 7 lines, but you need 6 other qubits, which are ancillas, which are used in the measurement of the so-called 4-way parity operators, which are these columns here, which check that these entangled states retain their property. And if they don't, there is a gate here, which is presented in these columns here, that restore the code in its original state. The advantage, of course, is that these measurements and the corrections are transparent to the qubit state. They work without knowing which state you are on. So they perform good correction of all the possible errors, except that you see you need, each time you want 1 logical qubit, you need 13 physical qubits. So that's a lot of hardware. But the main problem is that you have to, because you are employing 6 qubits here, sorry, 7 qubits, you have 21 error channels to monitor and correct simultaneously. So this is why this feedback circuit is rather complex. Now I'm going to turn to this other method proposed by Gottesman, Kitaev, and Preskill, and tell you about this wonderful grid state encoding. It's a marvelous idea, and really Emily has simplified my task enormously, because she has presented this representation of the state, the quantum state of a resonator, mnemonic oscillator. In our case, it's a cavity. And so I'm basically re-showing these slides. In the cavity, you have these variables Q and P, which are the like position or momentum, or if you are an electrician, you might think that you may think of Q as the charge, let's say, and P as the current. You have this all these photon states here, and their Wigner functions have these nodes. These white regions are where the Wigner function is 0, and you see each time you increase the number of photons, you add another white ring. But you have this other line of states where instead of adding photons, you displace the vacuum. That creates a superposition of Fock states, of which, of course, you can vary the displacement, but also you can vary the squeezing of the quantum fluctuations. And here I've represented squeeze vacuum in the diagonal direction, but you can squeeze along X, along the position coordinate or the momentum coordinate. The cat states presented by Emily will come at the very near end of the talk. So instead of superposing coherent states to create cat states here, we are going to superpose a squeeze vacuum. So that's the idea of GKP. Ideally you would infinitely squeeze your vacuum along Q, and you would superpose copies of the squeezed vacuum along Q, and you would use as many superpositions as you could, and creating this picket fence wave function. So this is a very anomalous type of wave function, which you do not really consider in quantum mechanical textbooks, but it has wonderful properties. If you can realize such wave function, it is marvelously suited to error correction. So in order to, the difference between the 0 logical and the 1 logical is a simple translation along the position coordinate by half a period of the picket fence. And you see immediately the advantage if you have some noise, if the position coordinate is shaking, it will take a finite amount of shaking until you confuse 0 and 1. If you have just a diffusive process, if you have a slow diffusion, you have time to measure this displacement, this overall displacement, which will not tell you which wave function you have, because you're just measuring an overall displacement. And you can correct before you go to half the distance between the pitch of the 0 logical and the 1 logical. So it's a great idea. There were two problems. First of all, no one knew how to create such exotic wave functions. And then there was also a lack of motivation due to the fact that in a cavity, in an oscillator, we're not really submitted apparently to displacement, we are submitted to photon losses. And it took the work of Steve Gerving and Liang Zhang to actually found numerically that this code is actually optimum also for photon losses. It corrects, of course, displacement, which random displacement, which apparently you don't have, but it is actually the best code for correcting also photon losses. So that was a very strong motivation for creating these wave functions. They were created for the first time at ETH Zurich in the group of Jonathan Home, but we at Yale used this idea to perform the first error correction algorithm using this idea. And in order to explain how this correction works and why what is really marvelous behind this code, you have to go back to the basis and really understand that when you consider translations in phase space, and here I'm choosing translation U followed by translation V, and then we return to the origin by this translation minus U plus V. Classically, when you return, you don't accumulate anything. You recover exactly the same state that you started from. But quantum mechanically, you actually acquire a phase which is proportional to the area. Essentially, it is the area divided by action quantum. And it is wonderful that this geometric property is exactly equivalent to saying that the position and momentum have a commutator equals to IH bar. We can write exactly this product of translation in another language where we introduce displacement operators where the argument is a complex number. The modulus of this complex number is related to the photon number associated with this displacement. Now there's a very important property. If you choose two translations cleverly with the right distance here and the right angle, you can make sure that they commute if the area they enclose is a multiple of the action quantum. And we're going to choose two action quantum here in this area to make an effective logical qubit. This side of this square here are called stabilizers. They can be measured simultaneously since they commute, and they play for the code of the role of the identity because the code, the states that we're going to use are periodic with this period. This is the period of the picket fence that I had presented. So let's accept that these translations here around this square are the identity of our code. Let's look at half these translations. So we have X here and we have Z. And of course, we have x squared equals to I, because if we do x 2 times in a row, we get this translation, which is the identity. And then we could do this diagonal translation. Now, Euclidean geometry tells us that if we have two action quantum in this big square, this triangle, which is bordered by x, z, and y, has exactly 1/8 of the total area, and 1/8 that gives you an I factor. And that's exactly the type of relation that determines the polyalgebra. So it's absolutely fantastic. We have 3 translations in the plane now, which play exactly the same role as the Pauli operators for spin 1/2. So you see that we can implement a qubit in this way. And the amazing thing also is that all the Clifford operations that you perform in quantum information will be tolerant in this kind of encoding, including the control knot that would couple to qubit. So you have to create and maintain these very funky wave functions, but if you can do this, then there's a whole world that opens to you that's very interesting. Now, this Picket-Fentz idea is a bit too ideal. In practice, we use what are called finite energy wave functions, which are not infinite Picket-Fences. They are just several pickets. And they have an overall envelope, which is actually the reciprocal, which has a width which is reciprocal to the width of the peak here. So this allows you to have a code with a finite energy, because you don't, your wave function doesn't extend to infinite distance to the origin. And the code can be represented in this Wigner function that was discussed earlier by this set of red dots, which have an area which is less than the vacuum, but nothing is violated because you have several dots. And in order to maintain these dots here, which is the location of the state in phase space, the simultaneous occupation of the states in phase space, you have to apply 2 types of forces, of correcting forces. There is a first set of forces, which are these blue forces, which maintain the sharpness of the peaks. But you have also to trim the envelope, because as you try to make the peak too sharp, you're going to extend the envelope and you don't want to have too many photons. So you need this other set of effective forces, which I have represented in purple here, which constrain the code to in a finite place around the origin of phase space. Okay, so that's the code, and we have implemented this error correction by this hardware that was presented by Emily. So the logical qubit is going to live in this high Q cavity, which is a post cavity, and we see the entrance of the cavity here in this picture. It is indicated by this red arrow here. So inside this block of aluminum, we have a transmon qubit, which is going to be the Ancilla. It is going to endow the cavity with enough nonlinearity that we can manipulate the states. And because the transmon is going also to be used in detecting errors, we need to be able to read out the transmon, and so there's also an auxiliary cavity, this low Q cavity, whose entrance here is this blue arrow. Okay, so let's flash a few characteristics. So we have nothing, this experiment has been realized by essentially off-the-shelf components which don't have a particularly impressive characteristic. And none of these numbers for people who work with superconducting qubits are particularly special. Maybe the important thing is the feedback. We measure the transmon in about 700 nanoseconds, so we can determine its state. And then we have fast electronics that in 300 nanoseconds are able to send a correcting signal back to the system. And with these methods, we use this kind of feedback loop to impose the effective forces that I was describing earlier, this blue set of forces and the purple forces. The main workhorse of the creation of these grid states is a new gate that did not exist before in circuit QED, which we call the conditional displacement gate. I call it a Swiss Army knife because it does absolutely everything. If you know how to do this gate, you know how to create the state, you know how to manipulate it, you know how to read it. You can do everything if you know how to do this gate. It's a very comforting thought. You have to do, it's a bit like in golf, you have to do one thing very well. Okay. So we start with the Hamiltonian of the cavity, which, and then the qubit. I am not really writing here the Hamiltonian of the cavity and the qubit. I have rotated them out. I am here writing only the coupling. So that's the coupling between the qubit and the Ancilla and the cavity. And then we have a drive here. We're driving the cavity, and that's this epsilon function. So we're going to drive both the Ancilla qubit and this GKP mode. Now we're going to drive the system in such a way that the Hamiltonian that is generated by this force epsilon here will, most of its part will be essentially echoed away, but there will be a remaining part that will actually be an Hamiltonian that generates a conditional displacement. So let me explain how does it work. How it works. So by the way, I forgot to mention that the way we get from this line to this line is by substituting by a change of variable, in which we change this operator A into a displaced A, which includes includes the effect of this drive epsilon. So we can look in phase space what happens to an arbitrary state. So here I have chosen a squeezed vacuum state, but I could have chosen any other Wigner function representation. And the gate, by the way, is inspired by work that has been going on in Irfan Siddiqui's group. So what we're going to do after having, for instance, prepared the qubit along the equator after a pi/2 pulse, that's just putting the qubit in a superposition of E and G. We are going to apply the following sequence. So we are going to, we're going to apply first the drive of the qubit in the positive direction and create this ramp, and that displaces the initial state. Unfortunately, depending on whether the qubit is E or G, it also rotates the state, which is a parasitic effect. But we can get rid of this parasitic effect by this double echo sequence, where we modulate the drive of the cavity and we apply a pulse on the qubit in such a way that the net effect after this sequence is a displacement of the initial state up or down, depending on whether the qubit is in E or G. And that's basically this conditional displacement gate. It displaces any state in the cavity in one direction by a certain amount if the qubit is in G, and it does the opposite translation if the qubit is in E. And we can tune the displacement and the angle. We can use this gate in reverse. We can use it to actually measure a displacement. So let me explain how this works. So suppose you had created one of these grid states, and then an error occurred, and it was displaced, say, to the right by this amount epsilon. By this circuit here, which includes this conditional displacement gate sandwiched between the two pi/2 pulses that I have shown, and followed by a measurement of the qubit of the Ancilla, we can realize a mapping of displacement into the state of the qubit along the equator. So this is how it works. So we for instance, place the qubit along X here, and then we apply the gate, and well, so essentially my animation for some reason is not working very well. Anyway, so after the contribution of these various peaks evolved for some time, they all are refocused, and basically this displacement epsilon is mapped into an angle along the equator of the qubit for the state, and by reading out either y or x, we can measure this angle theta and get 1 bit of information on this displacement. This is a protocol that was proposed by Barbara Terhal and her student. Okay, so you see the advantage of GKP is that if you know how to read the state, you know how to correct, because you see, in order to read the state, you have to read this displacement, but you can also use exactly the same function for detecting errors. So in order to actually demonstrate error correction, we had to calibrate this conditional displacement gate. And this is done by a Berry phase measurement, essentially. We create these loops in phase space, which will turn clockwise or anti-clockwise, depending on whether the qubit is ENG. And by reading the qubit at the end, we can get this beautiful Berry phase interference that you can fit here. This is the black curve. And then you calibrate basically the amount of displacement that you do in this controlled displacement gate. In order to stabilize, to fully stabilize the qubit and implement in phase space these two types of force, the trimming force and the sharpening force, you have to cycle through 4 units, essentially measurement of displacement followed by a feedback correcting displacement, which are these black rounded boxes. And if you repeat this continuously, you will essentially attain a steady state. So this is an example of what happens when you repeat those states. Here along the y-axis, you have a measurement of the stabilizers, which eventually converge towards a flat value. You see also oscillations in this value due to the fact that we apply these 4 operations in a cycle. After sufficient number of rounds to achieve a steady state, you can measure phase space, this phase space distribution. Actually, we do not in our experiment measure the Wigner distribution. We measure its Fourier transform, which is this C function here, but this characteristic function. But every information that you find in the Wigner function, when you have this kind of periodic lattice, you find just the reciprocal lattice for the characteristic function. So you get exactly the same information. So as you can see, we have indeed achieved these grid points in phase space. And I want to orient you. So what you see are here only the value of the stabilizers. These red dots are located at around the values of the stabilizers. So you see that the stabilizers have values close to 1, which is good. But what you are seeing here is the manifold of the logical. So you don't see any state in particular. You see a random superposition of the 2 states of the manifold. In order to isolate one particular state, you have to measure either Z, Y, or X, which are these locations that are indicated by these black points here. So this is what we do. We first stabilize, and then we do a measurement, let's say of X. And here we see we get a minus value here. So we actually, that creates the preparation of the minus X state. A pure state in phase space has 3 red dots for every blue dot. There's a proportion of 75% red and 25% red, as you can check in any pure state. So you see what happens here is a good indication that we have created a pure state, and we can by doing this kind of measurement, we can create basically all the states that we want. If we don't get the right X state, we can do a simple translation and get the right eigenvalue. But so in this way, we have prepared the X state, the Y state, and other states like the magic state that is important in Clifford operation. Sorry, non-Clifford operation. I want also to point out that I have presented so far what is called the square code, but there's another organization of phase space, which is called the Hexagonal Code, which puts X and Y and Z on the same footing. So for instance, in this encoding, you see the X state and the Y states are exactly the same. There's simply a rotation by 120 degrees between them. So again, let me show you the cell, the unit cell of the square code. That's this figure. For the hexagonal encoding, the unit cell is a diamond, which makes the distance between this stabilizer, and this stabilizer, the X, Y, and Z direction, all equivalent. And that, in a sense, is superior. So let me explain this kind of measurement of coherence. So what we have done here is to begin at time t equals 0 by preparing a state either along X see the decay of this state. We measure the operators and we see this decay. So this is a measure of the coherence along X, Y, and Z. And you see by these closed dots that in the square code, we correct very well the X and Z directions of the Bloch sphere. They live, of course, much longer than if you don't correct, which are these open dots. And they live for about 275 microseconds, which is longer than the lifetime of one photon in the cavity. Unfortunately, because Y is farther away, it includes more photons. If you wish, it decays faster. So for Y, we get an improvement, of course, with above no correction, but it's not as spectacular. Now, if you compare with the hexagonal code, in some sense, it is much better because now all the X, Y, and Z are corrected in exactly the same way. And you also have a sort of doubling of the lifetime when you do error correction. So error correction works. Unfortunately, the overall lifetime is a bit under the lifetime of one photon in a cavity. So this is what we call not really going to break even, because you could have encoded information using a superposition of 0 and 1 photon in the cavity. It would not be correctable at all, but that would be an encoding. And so what you have to do in error correction is that you can blow really past break even. You can correct. You can have your logical qubit be of much better quality than the best single qubit, physical qubit in your system. So that's a criterion that, of course, many labs are trying to achieve. Okay, I think my time is up. Just in 1 minute, I just want to say that there are very clever new proposals that would essentially suppress the need for feedback through the external electronics of the experiment. You could implement these forces that stabilize the logical qubit purely autonomously. This is a very nice proposal by the group of Steve Gerving. And it has been also realized experimentally in ion traps very recently in the group of Jonathan Bohm. And we can easily do it in superconducting qubit by actually an autonomous protocol that resets this Ancilla qubit totally autonomously. So this is a very clever idea, which actually concatenates two operations that I have chosen and suppresses the need for an external readout. Okay, so I have arrived at the end of my time. So let me summarize where we are. So with this JKP encoding, we are correcting all errors. So this experiment demonstrates that you can correct all errors simultaneously. This is very important. If you correct one type of errors, that's nice, but if you really want to prolong the lifetime of quantum information, you have to correct all errors simultaneously. Break-even is really the goal, that the sort of holy grail that many groups are pursuing. And it's not just break-even. You have to really go well past break-even. We would like to do something like 1,000 times break-even to really have logical qubits that would do many sufficiently many operations to do interesting quantum algorithm. But what I want to say is that nothing in our experiment was really optimized. So I think there's a lot of room, even in this simple experiment that I presented, to do much better than break-even. And this is, of course, what we're going to do in the next months. Then further on the horizon, there is this question of the gates between logical qubit. So you don't want to simply error correct one logical qubit. You want to error correct the logical qubits while doing logical operations on them. And in particular, you want to error correct while you are doing two operations that involve two logical qubits at the same time. And this is where this GKP code really shines. An operation, a Clifford operation like the CNOT, can be really done fault tolerantly in this code. So you could correct and do the CNOT together. And this is because the CNOT in this continuous variable implementation is a transformation that we know very well. So we have two oscillators with position and momentum, x1, p1, x2, p2. And what I have shown in this box is the kind of transformation you have to apply. You see, it's a linear transformation when you think about it in terms of displacement. And the merit of this type of operation is that it is essentially fully linked to two-mode squeezing, which we have done with the quantum limited amplifier. There is this field of amplification of microwave signals at the quantum limit done with the parametric amplifiers, and this transformation of this CNOT is exactly something that we know how well to do. So that is really what is called reservoir engineering. And so just if you do what this field can deliver, let's say on some a few years time scale, I think it's entirely reasonable that you could have these logical qubits with gate times of 100 nanoseconds and with cavities with a photon lifetime of 10 milliseconds, which would give you really the possibility of doing tens of thousands of operations. On that note, I would like to thank you for your attention, and I'll be happy to answer any questions.
Yeah, I have one about the Markov stabilizer protocol. Is it related to MCMC simulation, the convergence of the Markov chain?
Yes. Okay. So I see that your question must be on this part of the talk that I rapidly presented this So your question is, am I right in thinking that your question is about this slide?
Yes, and the next ones too, and maybe even the previous ones.
Okay.
I'm not experimentalist, okay, but you talk intrigued a lot of theoretical concepts that I am familiar with, and maybe there is a connection, and maybe there is some tricks of MC simulations where you do burnout of the Markov chain, and it's a little bit work of art to achieve that. And you demonstrated experimentally that you can achieve it. So there is some connection between theory and experiments that you describe. And I'll give you a compliment, you probably don't need it, but I observed that some good experimentalists know theory better than the theoreticians. You are one of them.
No, I am at times I am only an amateur theoretician. No, but maybe I can. I went very fast on this slide, so maybe it would help if I would explain it a little bit better. So I have presented previously this operation that allows you to get 1 bit of information on a displacement. So you measure the displacement of the wave function, and because you map this displacement on the qubit, at the end you get each time, for each measurement, you get 1 bit of information. Pretty much the bit of information you get is whether your wave function displacement is basically has happened to the right or to the left. And so by making these measurements, you can you have to, of course, do you have to do 2 axes. You have to measure at least along the position axis. So this is the Q direction or the P direction. And then you are correcting. So you get this 1 bit of information, and depending whether you have a +1 or -1, you're going to make a correcting displacement. So that's what this feedback loop is. But you have to also make these measurements in different, I think, with different resolutions, because you need to both sharpen the peak and trim the envelope. So this Markovian stabilization protocol, which, you know, only it's Markovian because it depends, what you do depends only on your previous measurement. We don't try to accumulate any memory of previous measurement. So it's this is the sense in which it's Markovian. By accumulating all these random bits and affecting the correction with 2 different magnifications and 2 different directions, this cycle basically maintains the code. That's it. Effectively, its overall effect, when you integrate over several rounds, it essentially maintains these forces in phase space. These blue forces that sharpen the peaks, and these purple forces that trim the envelope. I don't know if I have answered your question, but
okay, is this now fine-tuning in both directions?
Great. Maybe we can actually get some questions from other members of the audience. So Alp has a question that he put in the chat.
Okay, yeah, so I'll read it out if that's okay. Thanks, Michel. It was an excellent talk. So I have one question about kind of comparing the oscillator gate fidelities to the properties of the transmon itself. So in this system, it looks like the nonlinearity is reduced at the same time. You're also reducing losses at the same time. So both of these time scales are kind of slowing down, if I understand it correctly. So my question is, both nonlinearity and the loss is scaled down, so the time scales are now longer. But in the end, can you have a net gain in terms of gate fidelity compared with a gate you do on the transmon qubit itself? So if you take Ancilla induced dephasing and decay into account, is there a net gain?
Yes, this is an excellent question. And of course, yes, the answer is that you should eventually gain a lot. It's true, we slow everything down, the nonlinearity is smaller, but actually in this control displacement gate, we supplement this small nonlinearity by very large displacement in phase space. So the gate is not going to be much smaller than what you would get in a usual transmon. You see, so of course, this is a bit a caricature. I have displaced the squeeze state by only, let's say, twice its length. In reality, the number of photons that are involved in these displacements are very large. They are something like 10,000. So you can, even though you have a weak nonlinearity, so if you look at this expression, the chi here, which is rather small, is magnified by this alpha, which is very large. So we maintain pretty much for these gates the same type of time scale you would have with a regular transmon. I'm not saying that this scheme overall is easy, because you have to have these microwave pulses they need to be quite precise. So you need very good control electronics. But this is something that you have in, let's say, NMR spectrometer. So in NMR, you have exactly the same problem of control. Of course, here we are doing this thing at 10 gigahertz, not at a few hundred megahertz. So it's a hard electronics problem, but we think it's entirely solvable. So to summarize, yes, you would say that we seem to have slower time scales, but not really. So at the end, in my conclusion, I was saying that the gates would be around 100 nanoseconds. So when you think about two qubit gates, this is not enormous. If you think of the various implementations nowadays, 100 nanosecond for a 2 qubit gate is not extra long.
Thanks.
Okay. So I guess we have some other questions. Michel, how would you compare the long-term prospects for protocols like the one you talked about with, for example, like the surface code method?
Yeah, so I think that what we're proposing is looks like more that like the first layer of a surface code. What we're proposing is a method to get very good first layers, where the let's say the first layer of logical qubit will be very hardware efficient. So we don't need to spend too much hardware to realize the first round of error correction. But eventually, I think that the nice thing that the surface code has for it is that if you want to reach a very, very high level of accuracy, then you have to have an arrangement which is like the surface code or the color code, where you have several qubits that collaborate together to make logicals in this topologically protected way. that these codes offer. But you're going to have much less overhead if you start with the first layer of very, very good, very coherent qubits. It's just that, you see, it's very advantageous in this kind of lattice of the surface code or the color code to start with excellent qubit to begin with. So I will not say that the strategy here is to totally replace the proposals that involve some kind of topological protection using clever lattice properties. I think that you're going to be much better off if you start from excellent qubits to begin with.
Michel, maybe I can ask a question. I'll steal one from chat. Actually, I had almost exactly the same question. It's a question that Dan Stamperkern also asked. Is there an advantage in thinking about maybe replacing the photonic resonator with a phononic resonator? And is there some way one could imagine experimentally sort of, what the prospects for doing that might look like?
Yes, yes, of course, the phononic resonators, their advantage is that they are much more compact. But of course, at present, these cavities, they seem bigger. They are actually only a centimeter cube, and they could be flattened. Only one dimension of the cavity needs to be of the order of the wavelength. So you could easily have arrays of 10,000, 100,000 of these superconducting cavities if you would make them by microfabrication processes like the work that Rob Sholkov has demonstrated. For instance, you could stack wafers covered with superconductors and create very compact cavities in this way. Frankly, I'm not too concerned about the footprint or the volume of these cavities. I'm very concerned about the access wires. The fact that you need in all these implementations at least one access wire per qubit, whereas for, let's say, the chip in your laptop, you have, let's say, a few billion transistors and only 1,000 wires. So basically, there's a ratio of 1 to 1,000,000 between the number of wires and the number of nonlinear elements. We are very, very far from such an advantageous ratio. I think, to me, this is really the problem that we should address.
Okay, I see another question in the chat from Rob Cook. Is there anything to be gained by adding tunable coupling between the Ancilla qubit and the cavity? Well,
in fact, the gate I have presented is tunable in the sense it is really a gate with excellent on-off ratio because it is powered. Well, this is called the parametric gate. It is on. It is not on all the time. This gate is zero. It activates only when you simultaneously power the cavity and the transmon. So this is very different from a lot of other gates that are out there. It is a gate that couples things only when you simultaneously irradiate the cavity and the qubit. So this coincidence in signals gives you a very good on-off ratio. But of course, by putting, I think the question alludes to the fact that if you need even more isolation, you have to put in other intermediate stages in your connection, and that can be done also in this kind of implementation. But already this control displacement gate is very selective. maybe I should say the following. So what was the main limitation in this experiment was actually the T1, the relaxation process of the Ancilla qubit. So all the errors were dominated by the fact that during the measurement, the Ancilla can relax from one state to another, and that introduces back-action errors. And so something I did not mention, but the way we are going to circumvent this problem is by using another type of Ancilla. So instead of using an Ancilla transmon qubit, we're going to use a Kerkat qubit, which has the advantage of having two fully degenerate states. So it works great as an Ancilla for this kind of GKP encoding, because this kind of Ancilla would not have a back action on the logical qubit when you measure it.
Mm-hmm. Okay, maybe I can ask one of the more Outlook questions that are prepared by the Colloquium committee.
Mm-hmm.
So if you could assign a team to work on a different problem than what you work on in your group, what would it be?
Yes, so I think if you look at the state of this field of circuit QED, which has for me the charm is that it's a kind of Lego set. You assemble circuit elements, and there's an enormous amount of creativity that has been displayed by various groups, because you can actually take these elements and combine them in many ways. So this is a very charming aspect of this field. I think that we are beginning to see the problem looming is that in this Lego set, the parts are not quite perfect. And so there is so much combinations you can do before you are hit by a degradation of signal to noise ratio. You know, if you want to do more precise experiments, at some point, you cannot just combine these parts. You have to make the parts better. They have to have a better quality, because otherwise you accumulate too much of the defects. So if I had, if you give me the liberty to assemble a team that's going to be fully dedicated to this kind of project, that's what I would do. I am very confident, you know, these superconducting qubit elements that made incredible progress in the last 30 years or so. So you were kind enough to mention the work that we did in John Clark's group, measuring for the first time basically what was essentially a qubit, the levels of the Josephson junction, the quantum levels of the Josephson junction. At that time, if I remember correctly, the quality factor of the transition between levels was about 30. So which translates in in a nanosecond lifetime. And now there are groups that are announcing transmons with 300 microseconds T2. So we've had an enormous amount of orders of magnitude in improvement. But I think I don't see this stopping. I think we can do still much better, and this is becoming, I think, a priority. We know that we can do excellent. The Arroche group in Paris has done superconducting cavities with Qs of 100 billions. There's no, the limits that you would get from superconductivity itself are still not in range. So we should be able to have much better parts for this Lego game of circuit QED, in my opinion. And that would that would allow many more interesting experiments. There's, of course, quantum computation, but there's all kinds of other things like quantum simulations, for instance. So we have this competition, ongoing competition with the atomic physicists. And so I would use the resources that you would give me to get even better atoms.
Perfect. Yeah, on that wonderful note, let me it's about 1:40. So I'm going to ask Michel, I'm going to ask the PIs to step out. So this will just leave the graduate students and the postdocs and undergrads. I think I see an undergrad actually to hang out with you for a little bit. Thank you so much, Michel.
Okay.